The last application we looked at was a parabola in the construction of an arch bridge, and now we're going to look at another application of a parabola at a headlight. So if you were to take your car and look at the headlight, if you pulled it out, it would be like a big giant flashlight, and the concept's the same. So in this example, they say a headlight is being constructed in the shape of a paraboloid, and the word paraboloid is basically a 3D parabola. So that's what that means. With a depth 4 inches and a diameter 5 inches, as illustrated in the figure. Determine the distance D that the bulb should be from the vertex in order to have the beam of light shine straight ahead. What should the distance D be? Where should they put the focus? So really in this, when they're saying what is D, they're asking us in our formula world, what is the value of C, which is always the distance from the vertex or the center to the focus. So we have some headlight here, and so I'm going to draw my picture the way it is there. They said that there's some parabola, some headlight here, it's a 3D paraboloid, and so if we were to look at the front of our car, we would see the circle of our headlight, and so that's what this is here. So I'm going to introduce my coordinate system. Let me make my vertex just a little better. Right there, that's a little better. I'm going to make my vertex at the origin, and then let me write some things on here. It said that the headlight is being constructed in the shape of a paraboloid with a depth of 4 inches. This is how deep it goes into the car. So from here to here is 4 inches. So I can label a couple of points here. This is a point I could label, which is X is 4. I don't know what Y is. But I know that this is 4, and I don't know what Y is, okay, but we know that, okay. Then they also said that the diameter of the circle in the front is 5, okay, so that means across my circle is 5 units. All the way across the circle is 5, because that's the diameter. So half of the diameter is a radius, so that means from here to here is 2.5. and 2.5. So then I do know my my Y value. This point would be 4, 2.5, and this would be 4, negative 2.5, if this is my vertex. If it is, 0, 0. All right, because I have drawn my parabola facing left, right, then the formula that goes with this is the Y squared is equal to 4CX. And I didn't use the H or the K because I chose my vertex to be at 0, 0. So, all I got to do to write this equation is figure out what C is. We can do that by borrowing one of these points. So either one would do. I'll just go with the positive one. 2.5 squared is equal to 4 times C times the X value, which is 4. So I get 2.5 squared. What is that? Let me see if I already did this. It's 6.25. Is what this is? 6.25 is equal to 16C. To solve for C, I get that C in decimal is 0.390625, or in fractions is 25/64. That is the value of C. So they didn't ask me for the equation, but I could certainly write it. If I wanted to write it, I would say 4 times C right there. So I get Y squared is equal to 4 times C, which gives me, where did I write this down? Right here. 25/16 is what I got if I multiplied those two together. This would be the formula. But what they wanted me to ask is how far in do I put the bulb? Where is this? Where's the focus basically? What is this distance? They're calling it D, but we know it's C. And C is equal to 25/64, or this decimal. The units on that are inches, because that's what everything's in. So we could write a sentence that would say the bulb should be placed. The bulb should be placed 25 over 64 inches, or approximately 0.39 inches from the vertex. Okay, so that's a couple of examples of parabolas. Now let's take look at a couple of examples of hyperbolas. Okay, so one of the most important uses or applications of a hyperbola is that's how they construct the cooling towers for nuclear reactors. So that's a really big deal. That's one of the applications. Another one is they model the paths of comets, and then you can also do construction things off of them. So the couple of examples we're looking at is, one is the path of a comet we'll be looking at, and the other is a sports complex that they're building, that they're using architecture for. So let's look at those two, and that will wrap up this video on applications. The comet, let's read about it. It says, comets with a high velocity cannot be captured by the sun's gravity and are slung around the sun in a hyperbolic path with the sun at one focus. If the path illustrated by the graph shown is modeled by this equation, how close did the comet get to the sun? Assume the units are in millions of miles and round to the nearest million. Okay, so they give us this equation here. Looks like this. 2116x squared minus 400 y squared is equal to 846,400. Okay. Now we can make this look in standard form by dividing both sides by that, and we will in just a second, okay? But let's just sort of draw a picture of what's happening here. They said there's some comet that, and the sun can't quite grab it, so it gets slung around the sun, and the sun is at one focus. So I'm just going to draw sort of a parabola here, and this will be my center. And here's a focus, and here's a focus, right? This is a vertex, and this is a vertex. Okay. What I'm going to do is just look at one side of this. I'm going to ignore this side. So let's imagine that we've got this here, okay? The comet is on the path of the hyperbola right here, and it's getting slung around. This is the sun is right here at the focus, and this is the path of the comet right there. All right. So it's asked us, the path is illustrated by this, and it wants to know how close did the comet get to the sun? How close did the comet, which is this right here, get to the sun? Basically, they want to know what is this distance right there. That's what they want to know. How close do they come? Now, let's talk about what these other distances are. So maybe I'll kind of model my other part so we can just see our things. We know if this is the center, and it is, the horizontal distance, the way I'm teaching it, from the center to a vertex is A. And then the distance from the center to a focus is C. So this distance right here, what is this? It is C minus A. This is how close the sun is going to get to the comet. So we can figure all that out off of this. Let's get this in standard form by dividing both sides of this by 846,400. 846,400, 846,400. So this turns into x squared over 400 minus y squared over 2116 is equal to 1. Now this looks a lot more like a hyperbola that we're used to seeing. So we can figure out what A is in this instance and what B is in this instance. So A is equal to the square root of this. A is 20. B is the square root of this, and so B is going to be 46. And so for hyperbolas, it's the Pythagorean theorem. C squared is A squared plus B squared. So our C squared is going to be A squared plus B squared, and that is some big number. Where did I write it down? Did I write it down even? I think it's 2516. And if you take the square root, c is approximately equal to 50. 50 what? 50 million miles is what that's equal to. All right. What is A equal to? A is equal to 20 million miles. How close does the sun get to the comet? C minus A. 50 minus 20 is 30. So, we can write a sentence. The closest the comet will come to the sun is 30 million miles. All right, so that's that example. Now let's look at the sports complex, a construction example. It says in this equation, X and Y are in meters, and they give us this little picture. So I'm going to kind of draw the picture that they give you. It looks a lot like that one. It's a hyperbola. Goes like this. How do I say that? Okay, so they give us some distances in here. What do they say? Oh, two buildings in a sports complex are shaped and positioned like a portion of branches of a hyperbola by this equation. So 400 x squared minus 625 y squared is 250. All right. Now, they ask us a couple of things. How far apart are the buildings at their closest point? Okay, so in this picture, this is part of a building, and this is part of a building, okay? The closest they will ever be is, let me make this look a little more symmetric. I went out that far, let me go out that far. The closest these buildings will ever get will be right here, right? Well, if this is the center, remember the way I'm teaching it, the horizontal distance, this is A, and this is A. So the closest they'll ever get, closest the buildings will be is 2 times A. That's how we can answer the first part of this equation. All right, well, let's proceed. We have this equation, and we know we need to answer this, so let's go ahead. Let's get this in standard form by dividing both sides of this by 250. And when we do that very nicely, the way they constructed this problem, we get 625 in the denominator. We get 400 in the denominator, okay? And so right here we get that A is equal to 25, that's the square root of that. B is equal to 20. We can answer the first one. The closest the buildings will ever be, or the closest that the buildings are, is 50 feet apart, because 2 times 25. The closest the buildings are is 50, oh wait, is it feet or meters? Sorry, meters. The buildings come within 50 meters of each other at their closest point. The closest the buildings are is 15 meters apart. All right, that's part A. Part B, what did they ask? Part B said, find the distance D in the figure to the nearest tenth. So, in this picture, they have some distance over here. This distance, let me continue these guys. Some distance D here. Okay. This distance D. All right. But they tell us that this is 50 meters. So we can imagine, like we did in so many other examples, a point on our curve where the x coordinate is 50 and we do not know the y coordinate. So we can solve for y. So we have a formula that works very nicely here. So let's do that. Let's plug in our equation. So we've got x squared. I know my x is 50, so I'm going to say 50 squared over 625 minus y squared over 400 is 1, and I can solve for y. Let's see, that would be negative y squared over 400 is, if I make my 1 look like a 1 over 1, or 625 minus a 625, 50 squared is 2500 over 625. Okay, I can solve this and get negative y squared over 400 is a negative. Did I do it this way, or did I just do it all on my calculator? Let me do it this way now, because I'm doing it this way now. Okay, 625 minus 2500 is a negative 1875 over 625. All right, if I multiply both sides of this by -1, it's going to turn these positive. So that took care of my negative issue. I'm going to cross multiply and say 625 times y squared is equal to 400 times 1875. Then I'm going to solve for y squared by dividing by 625. And I get that y squared is equal to, let's see, 1875 times 400 divided by 625 is 1200. So y is approximately equal to the square root of that, which is 34.64. Okay, fine. That is how far this half is. But the total distance d is 2 times that. So if I take that and I multiply it by 2, that is 68. D is approximately 69.3 meters. That's how you can figure out what D is. All right, there's a few applications of our conics section.